Hi everybody, welcome to video notes 9A and 9B stoichiometry. So here are the objectives that we're going to be learning, 9A and 9B. So what is stoichiometry? So here's their definition. It's the mathematics of chemical equations. So we know how to balance them, we know how to write them, and we want to know things like, well, what if I start with 50 grams of salt and 3 crackers? How many Cheez-Its am I going to get? So we're going to need balanced equations, amounts of chemicals, what we're trying to find, and a periodic table. So to give you an analogy, let's talk about making tricycles. Here's the formula for making tricycles. So if I had an infinite number of tricycle frames, how many tricycles would Vanessa be able to make with 9 wheels? Well, you might look at it and say, well, 9 wheels will give us 3 tricycles. But we can do that with a little bit of math set up. So we have 9 wheels going in, and then there's 3 wheels for every 1 tricycle. So mathematically, 9 divided by 3 gives us 3 tricycles. Yay, tricycles, yay. Okay, so what we did is we used this balance equation. We used 2 of the things in it. We made a ratio, and we're able to compare and come up with that. Okay, so, oh look, it's an equation. Let's see if we can write a balanced equation for these particles. Okay, so it looks like we have 2 CUs reacting with 1 O2 to give us 2 CuOs. So what if we put in 1 O2? How many CuOs would come out? So we put one of these and we'll be able to get 2 CuOs coming out. Okay, what if we put in 4 O2s? If we put in 4 of these, then we'll be able to get 8 CuOs to come out. Okay. What if we wanted to make 22 of these? We want 22. Wow. All right. So I'll show you this one with a ratio. We want 22 CuOs. So how many Cus do we need? Well, it looks like we need 2 Cus for every 2 CuOs. And wait, what? We're going to need 22 Cus to go in so that we can get 22 CuOs out. All right, oh look, it's an equation in particle form. Can we translate that? Here we go. We have 1 N2, 3 H2s, and 2 NH3s. So if we want to make 6 of these, that's what we want, 6 of them. That's what we're given. What do we have to do? Well, we're trying to find how many N2 particles we would need. So we'd say, all right, I want 6 NH3s. And so it looks like there's 2 NH3s for every 1 N2, so I'm going to need 3 N2s to go in. Okay, that's how many we should use. So if we put in 21, this is what we're given, 21 particles of H2, and we want to know what we're trying to find, how many NH3 particles. Well, we say, well, there's 3 H2s for every 2 NH3s. Okay, so all I did was use these numbers here, and I find out that I would get 14 NH3s to come out. Okay, so what we're using these coefficients as ratios, and that's for particles, all right, but we can't even see particles, we can't even count particles. So what we're going to use is moles, because the coefficients mean moles. So did I say that the coefficients mean moles? Coefficients mean moles. So what do the coefficients mean? They mean moles. So we can use them as conversion factors. We can convert one chemical to another. We have to use the coefficients from a balanced equation, and the numbers are the coefficients in a ratio, and the units are moles of whatever we need. So here's some mole ratio examples. We can compare 3 moles of FeO to 2 moles of Al. So where did I find the FeO? There it is. Where did I find the Al? There it is. So that's moles of the stuff, and then the coefficients go in front of moles. All right, well, what about 3 moles of Fe? Okay, so I took the 3 and the stuff. Well, we got to look at the equation. Well, it's every 1 mole will make 1 mole of Al2O3. So the numbers are the coefficients, so we don't see there's a 1. All right, and the unit is moles, and the chemical is the identity of the chemical in the equation. We can flip these too. We can say 2 moles of Al, because there's a 2 there, will make 1 mole of Al2O3. So we can pick any two things in the equation, any two things, any two chemicals, this one and this one. We put the unit of moles, we put the symbol for the chemical, and we use the coefficients as the numbers for each of the things. So we can do, you try one, you try. So pick two of the chemicals and make a mole ratio. These are called mole ratios, mole ratio, mole ratio, mole ratio. Okay, so coefficient ratios are needed to change the identity of a substance. Those coefficient ratios work for changing moles to moles, but we can't change moles to grams with it because these are only for moles. The coefficients are only for moles. So moles to moles use coefficients. So let's do a practice problem. Here's what we're given in the problem. Given 1.2 moles of KClO3 react. We want to find how many moles of O2 are going to form. So we need a balanced equation. Good thing it just flew in. So find. So I like to list it out here. Given 1.2 moles of KClO3, potassium chloride. Find moles of O2. All right, so it's moles of one kind to moles of another, so I can use the coefficients. 1.2 moles, write down your given, and we're going to multiply by a mole ratio. So moles of KClO3 go on the bottom because I want to get rid of it. Moles of oxygen go on the top. Okay, I'm changing one kind of mole into another. Where do I get those numbers? If it's moles to moles, go get the coefficients. Find the coefficients. So what's in front of KClO3? A 2. All right. What's in front of oxygen? A 3. Okay. So then we would take 1.2 times 3 divided by 2, and we find out that we need 1.8 moles of oxygen will form. Okay, will form in this reaction. So we're predicting how many tricycles. I mean, it's not tricycles, but we did exactly what we would do with tricycles. Okay, next, all right, grams to moles, moles to grams practice. This time we're given 4.53 grams of KCl. We're asked to find grams of KCl, potassium chloride. This time, 4.53 grams KCl. We can't change this into this unless we're in moles, but this is grams. So we have to use that step we learned about in the first unit with the mass from the periodic table. So grams KCl have to change into moles of KCl. All right. So whenever it's moles of a chemical and grams of a chemical, the number 1 goes with moles, and then we go get the number from the periodic table. So the number from the periodic table is 74.55 grams. Periodic table. K plus Cl. All right. Now we're in moles, so I can put the moles I'm trying to get rid of, KCl, and turn them into the moles that I'm worried about or that I'm trying to find. Where do the numbers come from when it's two different kinds of moles? They come from coefficients. So here's in front of the KCl, 2, and here's a 2 in front of KClO3, potassium chloride. I'm not done until I get grams. So now I can change the moles of KClO3 into grams of KClO3. Now, where do the numbers come from when the chemical stays the same but the units change? And number 1 goes with moles, and then I go get the grams from the periodic table, and I get 122.55. And this is from periodic table. Yay. All right, so the math, I do 4.53 divided by 74.55 times 2 divided by 2 times, this is just showing where it came from, 122.55, and I get 7.45 grams. Excuse me, sneezy time, KClO3. Okay, so next question, find grams of oxygen given 58.6 grams of KClO3. All right, so 58.6 grams of KClO3 times, we go to get this from the periodic, grams KClO3 for every mole KClO3. So notice the chemical stays the same, so the number 1 goes with mole, and I go get the grams from the periodic table. PT, periodic table. Okay. Now, moles of KClO3 can now change into moles of O2. Where do I get the numbers when it's moles to moles? Up here. There's a 3 in front of O2. That goes there. There's a 2 in front of KClO3. So that goes there. Okay. Then I got to change moles of oxygen into grams of oxygen. Anytime it's the same chemical, then we're going to use the periodic table for moles and grams to change it. 1 mole for O2 goes to 32.00 grams because it's 16 times 2 from the periodic table. And then I do 58.6 divided by 122.55 times 3 divided by 2 times 32, and I get 4.82 grams of O2. All right. If 30.8 grams of AgNO3 is added to excess barium chloride, how many grams of barium nitrate will form? What? Well, we need a balanced equation. And so for that last slide, you can make sure you try it and you get the answer 23.70 grams of barium nitrate for the last slide. Okay. All right. So now what we're doing for this is we're learning something new. It's called percent yield. Percent yield. So we can use these kind of calculations to help us get percent yield. Percent is always part over total times 100. Part is what you get in the lab. Okay. Total is what stoichiometry or these calculations say we should get. So that's called theoretical or expected yield. Yield means product. Yield means product. So anytime you're asking about a yield, you're asking about something that comes after the arrow. So the total down here comes from a calculation given an amount of reactant that's converted to product. Yield means product. Okay. So percent yield has a formula that's the actual yield, okay, the part that comes from an experiment, divided by a theoretical yield, which is the part that comes from doing stoichiometry times 100, okay? So actual yields is either given in the problem or you make it in the lab. Theoretical yields is what we've been doing with stoichiometry calculations. So here is another balanced equation. This is what we're given, 1.85 grams of aluminum. And this is also what we're given, 5.12 grams of copper. What is the percent yield? So when you see this, we need to know that we're going to do an actual over a theoretical times 100. All right, so actual has to be a product. So this is going to be our actual yields. All right, but this is reactant. Aluminum's over here, so we have to use the 1.85 grams of aluminum and use stoichiometry to see how much copper would come out. This is like when we're talking about the wheels and the tricycles. So we have to use 26.98 grams of aluminum from the periodic table, gives us 1 mole of aluminum. So then from the balanced equation, we want to change aluminum, moles of aluminum, into moles of copper. Why? Because we want to get the theoretical yield of copper, we got to do stoichiometry for that. So what number goes with moles when it's 2 different kinds of moles? It's the coefficient. So 2 for aluminum and then 3 for copper. We're not done until we get to grams though. So 1 mole of copper, why am I only using 1? Because it's coming from the periodic table, gives me 63.55 grams of copper. So if I do this calculation, I find out that 6.54 grams of copper are going to be produced in this reaction if everything goes perfect. This is called a theoretical yield. In theory, if everything works out, this is how much copper we should get. Okay, so for percent yield, we would say the actual given in the problem, 5.12 grams of copper given in the problem, divided by what we should have gotten if everything went perfect according to the stoichiometry times 100. It would be 78.29% copper is our percent yield. All right, let's do another one. Calculate the percent yield. That's a percent yield of if 82 grams of methane reacts with excess oxygen to make 93.2 grams of carbon dioxide. So I'm given 82.0 grams of CH4. And I'm given 93.2 grams of CO2. So this is my actual yield because it's a product. See, product, right? And it's given in the problem. This I'm going to have to use for stoich. So I'm going to use that to get a theoretical, theoretical. All right, so 82.0 grams of CH4 times 16.05 grams of CH4. Now, if you don't know where I got 16.05, here's where I got it. From the periodic table, I added up carbon, hydrogen times 4, add. Okay, that's where I got it. And then moles of CH4 change into moles of CO2. All right, now, what do I put when I have moles of one kind and moles of another? The coefficients. I look there and I get a 1. I look there and I get a 1. Okay. And then moles of CO2 have to change into grams of CO2. So for every 1 mole of CO2, it's 44.01 grams. And this came from the periodic table. Woohoo! Okay, then I do the math. And I plug in 82 divided by 16.05 times 1 divided by 1. Don't have to plug that in. Times 44.01, and I find out that you get 224.8 grams of carbon dioxide. Am I done? No, because I want a percent yield. So percent yield is actual, which is our part, over theoretical, which is our total, times 100. The actual is given in the problem, 93.2 grams CO2, divided by the theoretical, 224.8 grams of CO2, times 100. And we find out that we get 41.5% yield of carbon dioxide. Wow. It's less than 50, but maybe that was a good yield for that reaction. Okay, so why don't we get 100% yield? The particles need to collide to react. It might not happen to every particle. Some reactants and products have transfer issues. Maybe when we were pouring or getting them together, some escaped or didn't, or stuck to the container. And then side reactions take place. So here's the review. Always go through moles. Moles to moles ratios use coefficients from the equation. You can change reactants to products, reactants to other reactants, products to reactants. Percent yield is what you get in the lab, actual, divided by what Stoich says you should get, which is theoretical. All right. And then stoichiometry helps you get the amount of product expected in theory. Always go through moles, part over total. Total comes from doing stoich. All right, here's the objectives again. Here's our last thing, and